Batch 3 of Data Science A section. My ATT topic about PDS is data reorganization of refetching of pointer based data structures. Let's get into introduction of this topic. Rapid increase in process speed as far slower increase in memory speed has led to memory access times that far exceed the cost of simple algorithm operation and ambiguous hardware solution. Is this problem is a memory cache? See the cache memory and sidebar, which is exploit program local locality is to reduce the average latency. Other techniques such as prefetching, multi-reading, non-blocking cache, and dynamic instructions and scheduling the speculative exclusion and use complex hardware and software to further reduce or hide the high cost of memory access. And despite this mechanism, the processor memory gap currently requires a hierarchy of two or more caches between the processor and the memory. The wide range of costs of finding data in this hierarchy undercuts the fundamental RAM mode as assumption that all memory access have unit cost, which is a model most programs use to understand and design the data structures and algorithm. This divergence between the theory and practice and underlies many performance problems, and programming language also evolved. Early languages such as Froglet and store data in array structure. Later languages such as Simula, Pascal, C and C++ supported a pointer, which as facilitated writing programs such as database and operating system take a extensive use of pointer structures with their dynamic nature and reliance on heap allocated storage. Pointer structures have the fewer regular access patterns that do array and pointer manipulating application. Many of these techniques are fundamentally limited by their focus on the manifestation of the problem memory latency rather than on its cause, poor reference locality. In general, changing a program's data access pattern or a data organization and layout improves reference locality, compiler and analyze array access and the performance transformation and reorder these access without affecting the program results. Compiler use two array structure properties to reorder the access: uniform random access to the array elements and the number theoretic basic of statistically analyzing data dependency. Pointer structure however share their either property. For example, a key search in a tree structure must start at the root and flow 3-node pointer on the appropriate leaf of the tree. Generally, it is impossible to reorder these axes. In addition, although there has been a process in involving pointer analysis techniques, they are rarely guarantee that reordering pointer axes will not affect the program's result. Pointer structure consists of separate independently allocated pieces, and they possess the powerful property of location transparency. Because of this location transparency, the pointer structure can place elements in compound data structure in the different memory and the cache locations without changing a program's systematics. The careful placement of structure elements provides essential mission of improving cache locality of pointer manipulation program and constantly their performance. Cache memory. Cache memory is a contracted to be a small to ensure high speed access. The cache capacity is much smaller than the main memory capacity, and the astronomized is a high cost of accessing a main memory. The system transfer data is cache blocks or lines. These units encompass the multi words, typically 16 to 128 bytes to limit. Look at the picture to get an idea of cache memory associativity. The blocks the cache simultaneously searches. The cache typically constrains the block placement to 1, 2 or 4 cache location. The cache associativity is the number of location where it can place a block. Picture 1a blocks a design of constraint and programs misread the fraction of the total number of references that miss in the cache and thus must access the main memory, often characterize its cache performance. High miss rate indicates the poorer cache performance. The following formula gives the average memory access time for the machine architecture, which a cache access time is equals to cache hit time, cache miss rate into cache miss plenty, because the underlying hardware determines cache hit time and miss plenty. Reducing the cache miss rate provides a primary opportunity of software rights to improve a program's memory performance. It is sometimes useful for architecture cache miss as a compulsory miss which occur with when a data item is first loaded in the cache. The capacity misses which would generate it hits and large cache and conflict misses with the result of limited cache associativity and a rise from the different blocks mapping to the same position of cache. Programs can combine and these general data placement design principles, clutters, colors and compression to produce a catchy fusion data structures. Clutters packs two data structure elements that a program is likely to access at the same time in the cache blocks, thus improving spatial and temporal locality and providing the implicant prefetching. For example, an effective way to cluster a tree is to pack a subtree region into a cache block for a series in a subtree clustered in a cache block. The unexpected number of access to the block is the height of the subtree to log 2 of k1, which is greater than 23 in the case of deep the first cluster scheme, where k nodes is a block from single parent and child grandchild chain and expected number of access, and the block number 3 search is bounded by 2. This analysis assumes a random access pattern for the specific access pattern such as the depth first. Such other cluster schemes may be better in addition. The tree modification can destroy locality. However, our studies indicate that of tree that changes infrequently, subtree clustering is more efficient than the allocation order clustering, which places and contemporary allocated tree nodes in the same cache block. Coloring cache can finite associately only on a limited number of concurrently access the data elements can map to the same cache block without causing conflict misses. Coloring places elements in memory such that elements accessed at the same time map to non-conflicting cache regions. Figure 2 shows to the two same scheme which can each set containing there is a associativity blocks into two regions P set and CP set. The coloring uniquely maps the frequently accessed structure elements to the first cache region so that they do not conflict with each other, whereas it maps the remaining elements to other regions. Such a mapping avoids conflicts among heavily accessed data structure elements and prevents infrequently accessed elements from replacing them. In addition, if the gaps in the virtual address space that implement coloring are multiple of the virtual memory page size, this scheme does not waste any physical memory. Compression data structure elements let more element clusters in a cache block increases the cache block utilization and the shrinking and the structure's memory footprint, thereby reducing the capacity of conflict misses. And compression typically requires a computation may be cheaper than the additional memory reference. Structure compression methods include data encoding and techniques such as key compression and two structure encoding techniques such as pointer elimination, which replaces a pointer with computed offsets in the conflict heap data structure. A classic example: store a nodes of children at known offset in another. Hot cold structures splitting, which works which because most data structure search examine only portion of individual elements until they find a match. Structure splitting separates heavily assessed hard portion of data structure elements from rarely assessed cold portion. Although this technique increases the total size of data structure slightly, it can be significantly reduce the size of hot work. Catchy conscious data placement strategy. Although catchy conscious pointer structure design offer important performance benefits, this approach is difficult for average programmer because it requires a complete understanding of an application code and data structure knowledge of underlying catchy structure. Sometimes many programs are unfamiliar with and significant rewriting of application code. Here is a catchy memory and conscious definition. Look at this flowchart and the step-by-step case sensitivities of catchy memories. Here is the address of these problems and changing, modification and rearranging of these structure layouts of catchy conscious reorganization, transfer of pointer structure layout in a linear memory layout and sequenced according to the expected data access pattern and map structure elements to reduce the catchy conflicts, and the reorganizer obtains the expected access pattern from the program profiles for external pointer structures such as tree. The reorganizer can glean the access information from data structure topology. Figure 3 shows how to combine various strategies to produce catchy conscious data structures. Structure definition, structure splitting and field reordering. To catchy conscious definition techniques can improve a program catchy behavior. Figure 4 shows the relationship of a catchy conscious definition techniques and the size of the structure elements. The three responsibilities depend on the size of the structure element related to the catchy block size and structure splitting. Many Java objects are comparable in size to catchy block, and case 2 is figure 4. Here is a type safe and statistical analysis of the data structure splitting and definition. Field recording and field legacy of applications of catchy blocks and splitting ineffective reordering the structure field to place those with the high temporal affinity in the same catchy block can improve catchy block utilization, and typically program group binds and large structure conceptually and may not be conferred for the temporal access pattern. And unfortunately, the logical order structure refers to the interactive poorly with the program's data access pattern, resulting in the unnecessary catchy missing. Compilers of many languages are constrained to follow the program missed supplied field order and therefore cannot correct this problem. There is a structure allocation of program to allocate the data structure element with a little concept of memory hierarchy, often resulting layout with interactive poorly with an additional parameter that pointer and exists. Here is the syntax for the data structure element that the program is likely to componentially the element is allocated, such as nodal parents and allocation of 5. Here is a hierarchy and memory hierarchy for L2 and L3 and 64 byte and 167 megabytes of Sun Ultra servers of E 5,000. Significantly few programs of catchy conscious data placements and structure reorganizing structure memory layout to correspond with its access pattern in comparently opposed to catchy conscious allocation. All through perform conscious conscious allocation is of data access pattern of 5 6. However, the trees are important class of structures possessing an topological properties that permit catchy conscious data reorganizing without profiling. Is a transparent copy and the detail about the phase of garbage collection and the topology based structure reorganization. C support unrestricted pointers and analytical techniques cannot precise invalid and add list structure patient quote from the olden healthy Beck mark Tiffy all pointers to all the structure element. Without this knowledge element system cannot move or reorder data structure without an application cooperation as it can in a language design or garbage collections. However, if a program is guarantees the safety of the transformation of the catchy memory. Here is in terms of the organizing operands and the Crotchal or reorganization, catchy conscious tree organization applies the sub-tree clusters to the entire tree. The reorganization allocates the top levels and frequently access the elements of the tree map of tree portion of catchy of lower level tree nodes and infrequently accessed elements cannot display them. Profile based structure reorganization. A catchy conscious data layout based places an object with a high temporal affinity near one other so they can reside in the same catchy block. In the accessible garbage collector uses profile data gathering and execution to optimize execution rather than subsequent one. The rarely on a property of object-oriented program. Most objects are small to refer and low overheaded and rely time and profiling transversal affinity graph to produce a catchy conscious data layouts. While copy objects the technique is automatic and requires no program intervention and experimental results for the several object oriented program show that this catchy conscious data place techniques and 16 to 42% and improves program performance by 10 to 37%, including real-time data profiling overloading 3 to 6. Further, we used one processor of 167 MHz and Sun Ultra server and E1065 compares the catchy conscious copy scheme of Wilson-Lamb model algorithm. This earlier algorithm attempted attempted to improve the program virtual memory locality by changing the transversal algorithm. The result shows the show to the our catchy conscious object layout techniques reduces the catchy programming. I hope you all have understood about the catchy memories and other algorithms of the data reorganization and fetching pointer based data structures. Here I conclude my about elaborating my topic. Thank you.